Let's talk about summing the terms of a geometric sequence. Okay, so again, recall that for a geometric sequence, we have A1 times R, A1 times R squared, A1 times R cubed, and this continues where we have the general ith term, and this continues up to some general nth term. Now note that that subscript I and n both have one subtracted from them in the formula because this actually starts at the 0 power. So this is the n equals 1 term, and it has the 0 power up there. So that's why all the subscripts are off by 1 in the formula. Okay, so what we're talking about doing is we want to add these values. A1 plus A1R plus A1R squared plus A1R cubed plus A1R to the fourth plus dot 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 plus A1R to the I minus 1 plus dot 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 A1R to the n minus 1. We'd like to add all of those up. So in order to do this, we're going to have to do something clever. So I'm going to let S equal the sum A1 plus A1R plus A1R squared plus dot 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 all the way up to A1R to the n minus 1. This is the sum of all the terms, or the sum of the first n terms. Maybe n is 10, maybe n is 100. I don't know how many terms we have. We have n of them. And that's what that sum looks like. Now we're going to do something clever. We're going to create R times S. So that's R times this entire right side and what we're going to do is we're just going to distribute. And that shouldn't be too hard. That's going to give us R times S is A1 times R plus A1 times R squared plus A1 times R cubed plus dot 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 all the way up to the n. And now this is AR to the nth power because it has exactly one more power of R. So these two terms correspond with one another. Now what we're going to do is we're going to use a technique from chapter 8 called elimination. We now eliminate. Let's call this equation number 1. Let's call this equation number 2. And we're going to take equation 1 and subtract equation 2. So what we get is S, which is equal to, let me copy and paste this guy, duplicate, minus RS, which is equal to this expression up above. I'm going to stagger it a little bit. I'm going to erase some of this here. Let's see. I'm going to erase this term. That's in there somewhere. But I want to arrange this so that these guys are stacked. Whoops. No, let me leave that like so. Now, this is a little bit intuitive here. If I move this term over just a little bit, What's the term that comes right before it? Well, it's going to have an A1. It's going to have some power of R, but that power is going to be 1 less. That's the term that comes right before it. So hopefully everybody's with me on that. Let's see here. Okay, this is the previous term. And now when we subtract, what we're going to get is as follows. So these terms will cancel. These terms will cancel. All these terms in between will cancel. This term, the last term in the upper row will cancel. And the second to last term in the bottom row will cancel. And what we're going to be left with is an A1 from the first row and this A1 R to the n from the last row. But because we're subtracting, it's going to be a difference. So what we have is S minus RS is equal to A1 minus A1 R to the n. Now, to find this sum, we're going to solve for S. Okay, so we can factor out an S. This is S times 1 minus R. On the right side, we can factor out an A1 and get 1 minus R to the n. And it turns out that the sum of all these terms is A1 times 1 minus R to the n divided by 1 minus R. And this is the sum value of the first n terms of a geometric sequence. That's our big formula for this one. So let's do an example of that. Example. Let's see here. Find the value of 3 minus 3 halves plus 3/4 minus 3/8 plus minus ... plus 3 over 256. So the first thing that we need to do here is we need to find a pattern. So what is the general ith term here? Find the pattern first. So let's see, we can rewrite this as alternating. So first we might want to note this is alternating, and the numerator is always, so it's alternating. The first term is positive. That's going to be important for us. The numerator is always 3. The denominator is powers of 2, starting with 2 to the 0. So I can rewrite this as 2 to the, oops, let me erase that. 2 to the 0 power, 2 to the first, 2 squared, 2 cubed, right on down the line. And this is 2 to the 8th power. So it looks like we're going to have a total of 9 terms. 0 to 8 is 9. So let's see. When I equals 1, we have positive 3 over 2 to the 0. When I equals 2, we have negative 3 over 2 to the first. When I equals 3, we have positive 3 over 2 squared. When I is 4, we have negative 3 over 2 cubed. And we need to find a correlation between this index and the part of each term that is changing. So, because it's alternating, we're going to use a negative 1 to the n, or negative 1 to the n plus 1, whichever one starts out positive. So this one is positive with n equals 1. So I think that this is the one that we're going to use. You liking these McDonald's colors? Oh, man, it's time for Big Mac. Secondly, the numerator is always going to be 3. And the denominator is a power of 2, but when the power is 1, when the index is 1, the power is 0. When the index is 2, the power is 1. And so whatever the index is, the power is going to be 1 less. And so the ith term here is negative 1 to the n plus 1 times 3 over 2 to the I minus 1 power. That is our formula for this. So when we go to add all of these terms up from I equals 1 to 9, and it's going up to 9 because this last power is 8, and this is I minus 1 is equal to 8, which means I is equal to 9. And we're going to add up negative 1 to the n plus 1 times 3 over 2 to the I minus 1 power. That's how you write this sum. But that's not what it's equal to. It's equal to our formula here. If we go back up, this is the value of the sum. This is equal to S, which is A1 times 1 minus R to the n over 1 minus R, where A1 is the first term, which in this case, the first term is 3. R, the common ratio, is what we're multiplying by each time. And so this is times negative 1/2 times negative 1/2 over and over and over again. That looks a little bit busy up there. But we get to the next term by multiplying by negative 1/2. And apparently, we're going all the way up to n equals 9 as our last term. And so what we have here is 3 times 1 minus negative 1 to the 9th divided by 3 times 1 minus negative 1/2 to the 9th divided by 1 minus negative 1/2, which is 3 times 1 minus negative 1/2 to the 9th divided by 3/2, which is 2 times 1 minus. If I raise a negative number to an odd power, it will become positive. It'll be 1 over 2 to the 9th power, which is 2 times 1 plus 1 over 512, which is 2 times 513 over 512, which is 513 over 256. So 3 minus 3/4 sorry, minus 3/2 plus 3/4 minus 3/8 plus minus dot 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 plus 3 over 256 is equal to this value here.